Hello everyone, welcome to my channel. In this lecture, we will discuss about the Ponchon-Savarit method with the help of ASPENHYSYS. We will determine that how much the Ponchon-Savarit graphical method is close to the ASPENHYSYS result. This is a problem, and in this problem, we have to determine the number of trays and the condenser as well as a reboiler duty with the help of Ponchon-Savarit method. We have a mixture of ethanol, which is 30 mass percent ethanol and 70 mass percent water. The top product should be 88 mass percent uh, alcohol, which is ethanol, and the bottom should be about 4 mass percent ethanol. The feed which is entering to the distillation column is at 40 degrees centigrade, and its mass flow rate is 5000 kilogram per hour. The reflux ratio in the distillation column is about 1. So in this method, this is a Ponchon-Savarit method. It is required that find the ideal trace using this method, and the second part is find the heat duty of the condenser and the reboiler duty. So this is a graphical method, and this is the enthalpy of the liquid, enthalpy of the vapor, and this is the X and Y, uh, the component in the liquid and gas phase, vapor phase. This is a method here they can obtain the feed flow rate in the kilomole per hour here. So they obtain the distillate and the bottom molar flow rate, and then with the help of this method they obtain the feed and bottom molar flow rate. So from in this method, uh, this is the Ponchon-Savarit method. So here you can see the XY and the enthalpy of vapor and liquid, and this is the equilibrium line and the operating line curve. So from this method, there are 10 number of stages, and the feed stage is 7th number tray is the optimal feed tray. So from the Ponchon-Savarit method, they have determined the reboiler duty and the condenser duty. So for this problem, the condenser duty is 3.16 multiplied by 10 raised to the power 6 kilojoule per hour, and the reboiler duty is 3.826 multiplied by 10 raised to the power 6 kilojoule per hour. In this lecture, we will determine the condenser and reboiler duty for the above problem with the help of Aspen HYSYS. So we will use the feed tray 7, and we will use 10 number of tray in the distillation column, and we will obtain the condenser and reboiler duty with the help of ASPENHYSYS. And after that, we will see that how much ASPENHYSYS results are closer to Ponchon-Savarit graphical method. So first of all, we will go to the ASPENHYSYS, open the ASPENHYSYS, click on new and click on create new case. So click on new, it will take some time. So this is the component, click on add and add the component. So here we have two component, click on add. Okay, this is the reaction sheet. We don't want reaction sheet, so we will click on component and click on add. So here we have ethanol and water, ethanol and water. So we will delete this reaction sheet because there is no reaction, so we will delete this one. Okay, now this is the component list. You select the component. Now go to the fluid package and select a fluid package. So I'm assuming the NRTL package for this. You can use another package. I'm using the NRTL, non-random to liquid package. Go to the simulation and go to the separator. This is the distillation column, and this is the stream, material and energy stream, material stream, and this is the energy stream. Click on drag and drop the material stream, close the split window, and double click on feed number 1. stream number 1, which is feed. So in the question, it is shown that the feed is at 40 degrees centigrade. Here in the question, you can see that the feed is at 40 degrees centigrade, and this is the mass flow rate of the feed. So the feed is at 40 degrees centigrade, and the feed is at 40 degrees centigrade, and its mass flow rate is 5,000 kilogram per hour. The composition of the feed is composition is given to us, and it is 30 mass percent ethanol. So 30 mass percent ethanol, 0.3 on mass basis, composition on mass basis. Click on this one, and 30 mass percent is ethanol, and the remaining is water in the feed. Click on OK. Now let's show unknown pressure. So the feed is suppose liquid. You can either use the phase fraction 0 because it is liquid, or you can assume the pressure. So I'm assuming 1 atmospheric pressure. The feed is entering to the column at 1 atmospheric pressure. Okay. Now double click on the column. You can rename the column, but I'm leaving it. Now this is the condenser stream, condenser energy. So it is QC condenser, and this is the reboiler duty. Okay, this is the bottom stream. Here you can see this is the bottom stream, and the condenser is total condenser. This is the top product, which is T1, and this is the condenser energy QC, and this is the reboiler energy. Okay, the feed I'm adding my feed, so this is the feed. Okay, the feed is inlet to the column at stage number 5, and there are total 10 number of stages. And this is the reboiler energy. Okay, uh, click on next. So the reboiler is once through reboiler. Okay, click on next. The condenser pressure, I'm assuming 1 atm pressure for the condenser and 1 atm for the reboiler. Click on next, and these are the optional, the condenser and reboiler temperature. ASPENHYSYS will calculate this temperature. So we have no value of for these. We will leave them. Click on next, and the reflux ratio is given to us. It is 1. It is given in the question. Click on done. So now, as you can see, it is unconverged because the degree of freedom here is not 1. Here you can see degree of freedom is 0, but we have no distillate rate. If we have distillate value, then it will be okay, but we have no information of this. But we have information about the composition of the ethanol in the top stream. So the composition of ethanol in the distillate is given to us. It says that it should be about 88 mass percent of ethanol in the top product. So 80 mass percent ethanol, and the bottom should not contain more than 4% alcohol. So the bottom should be largely water, and the top should be about 88 mass percent alcohol, which is ethanol in this case. So it should be 88. So we will go, this is go to the monitor and click on add specification. We have specification about the component fraction. Click on add, and here the top stage is the condenser in the column. So the condenser is the top of the column, and the component is given in the mass fraction. And which component is given in the mass fraction? The alcohol, the ethanol is given in the mass fraction, and its value is also given to us that it should be 88 mass percent in the top of the column. So it is 88 mass percent. Okay, close this one. Now now we have 0 degree of freedom, so click on run. So it will take some time to solve this problem. So it is taking some time. We have also given another information. You can also add another specification for the mole fraction of the ethanol in the bottom product in this area by adding the component specification, but I'm leaving the other. So this is the it will take some time. So here you can see it will create some problem. So it is taking some time. Let's see whether it converge or not. Uh, it can be converged. It is taking some time. Here you can see. Let's add the let's. I'm stopping this one. Click on stop, and I'm adding the other specification like the component fraction of the uh, ethanol in the bottom in the reboiler. The mass fraction of ethanol in the reboiler should be about 0.04. It should be 4%. Here you can see it should be not more than 4% mass fraction of alcohol in the bottom stream. Okay, now let's check this one. Now close this one, and here I'm let's cancel this one, deactivate and activate this one, and let's so this is the ethanol. Here you can see ethanol. Okay, so here you can see uh, here it is converged. So now we will go to the close this one. Okay, now here you can see the condenser duty. The condenser duty. The condenser duty is 3.224 multiplied by 10 raised to power 6. And the reboiler duty is here you can see. So this is the QR. So I'm attaching my QR. Close this one. So this is the parameter. Okay. So I will add attachment. Okay. I'm deleting this one. And double click on it. So here you can see this is the reboiler energy. This is QR. Okay. Now close this one. So here you can see this is the reboiler. So the condenser energy is 3.224 and this is the reboiler 4.242. So in the question, the condenser and reboiler duty it is given to us 3.16 and here you can see 3.224 and here this is the 3.242. So the reboiler energy is quite higher than the condenser energy, and here you can also see that it is quite higher than this energy, and there is little difference, some error. So this error can be uh, the feed plate, because the feed plate here is 7 and we assume the feed plate number 5. So I'm assuming my feed plate to be uh, 7. So the inlet feed plate should be 7. Suppose I'm entering the feed plate to be 7. Okay, and now so it shows some error. Here you can see it shows some error. So it shows some error. Now double click on this one, and here you can see it shows that it is unconverged. It is unconverged. It shows some error. So let's click it again on this one. So it is converged. Okay. Now check the value. So here you can see 3.117. 3.117. And here you can see 3.16. So it is close to this one. And here 3.826. And this is 3.131. So This can be this difference can be due to the fluid package because we assume the NRTL, and this graphical method. Uh, so this Ponchon-Savarit method can use another equation of state. So I'm using the NRTL method. So this is the reboiler and condenser duty. Now we can also uh, some draw some plots like what will be the effect of the fluid temperature on the top and bottom composition. So here we will go to the case study. For example, case study, click on add and the independent variable. So this is add the independent variable. So for example, this is my field, this is the independent, and the field temperature is, suppose this is the temperature. Field temperature is 40 in this case. So this is the 40 degree is the current value and my dependent variable. So this is the bottom. So the bottom and the composition of the ethanol in the bottom. So here you can see the mass of friction, the component uh, mass friction ethanol in the bottom. So in the bottom. So here I'm clicking at this one. So here you can see the ethanol mass fraction in the bottom is 4%. Okay. Now click on the case study. So my current temperature of the tube is 40 degrees centigrade, and suppose I want to start this simulation from 20 degree, and I am finishing my simulation at 45. So suppose if the feed temperature is 20 and ending at 45, then what will be the effect of this changing feed temperature on the composition of ethanol in the bottom stream? So the stage is the step size is suppose 5, and the it has 6 step calculated by ASPENHYSYS. Click on run. So click on results. These are the results table, and this is the plot. So here you can see this is all plots. Click on case number 1. So for clarity, so here you can see if we increase the field. So this is the this is the 20, 25, 30, 35, and 40 and 50 degrees centigrade. So here you can see when we increase the feed temperature, the temperature of the feed stream, then the mole fraction of the ethanol in the bottom stream is increases. Here you can see it increases up to 30 degrees centigrade. Here you can see, and after 30 degrees centigrade it decreases. Here you can see. So we should use 30 degrees centigrade for our feed stream. So feed stream, if our feed stream is at um, so here you can see the mole fraction of ethanol, and here you can see the mole fraction of ethanol in the bottom stream is unwanted. It is undesirable product in the bottom stream. So we want very less ethanol in the bottom. We want suppose we want very less percentage of ethanol in the bottom stream. So in order to get lower concentration of ethanol in the bottom stream, we should use feed which has a very which has a small temperature, which is at low temperature, suppose 20 degrees centigrade. So 20 degrees centigrade temperature is okay in this case because it gives us very low concentration of ethanol in the bottom stream, and we can get higher concentration of water in the bottom stream with the help of this case study. Similarly, you can also check other value, like suppose this is the independent variable. Click on this one, and suppose this is the column. Suppose this is the column diameter. Suppose the column diameter. What will be the effect of column diameter on the purity of ethanol which is coming out from the top of the distillation column? So click on this one and click on the uh, dependent variable. So the composition, this is the top product, and the ethanol composition. So composition of ethanol, and here you can see the component mass fraction of ethanol, and click on this one, click on done. Okay, now go to the case setup. So the diameter of the my distillation column is currently 1.5 meter. So if I change it from 1 to 2 meter with a strip size of 0.1, so it will give us 11 strips, 0.1, 1.1, 1.2 up to 2. So it gives us 11 strips. Now click on the run button. That is taking some time. So these are the results in table form. Here you can see the minimum and maximum values, and this is the plot. So here you can see uh, this is the plot. So the diameter and the ethanol composition. Here you can see the mass fraction of ethanol in the top product, in the top stream. So here you can see uh, the composition here is quite high, so we should use a very small diameter distillation column in order to get the higher concentration of the ethanol in the top stream, which are coming out from the distillation column. Thank you very much for your attention. If you are new to this channel, please like and subscribe, and thank you very much.